Okay, so my name is Yanan, and I'm an assistant professor at the University of Rochester. So today I'll be introducing Secure GPU for AI. So the goal of this project is to secure scientific AI research from GPU memory safety vulnerabilities. So we know the memory safety problem on the CPU side, the problem, the consequence, and even the solutions have been very thoroughly studied. But on the GPU side, we believe memory safety just has been overlooked for a really long time. And these days, scientific AI research heavily rely on GPUs to accelerate their workloads, right? Especially with the larger and larger language models developed, it puts a lot of pressure on the hardware resource, on the capability of the computing hardware. And when memory safety vulnerabilities exist in scientific AI workloads, the consequences could be very significant. For example, in our preliminary studies published in Usenet Security 2024 and Oakland 2026, we found that memory safety attacks can result in like data breaches, data integrity problems. And in the worst case, it can put the entire computing system, not just the GPU part, actually the entire system under security risks. So with that being said, we believe it's really important today to secure scientific AI research from GPU memory safety problems. So to achieve this, in this project, we have two thrusts. So the first one is about detecting and repairing the vulnerabilities in scientific AI programs. So through preliminary studies, we found that a lot of the scientific AI workloads are actually developed on top of commonly used AI toolkits like PyTorch and TensorFlow. And after looking into these toolkits, we found that unfortunately the GPU programs in them actually have many memory safety vulnerabilities. So the problem with the current situation is the community does not really have a developed detection and repairing tool to solve this problem. So in the first thrust, we're proposing the first fuzzing-based vulnerability detection tool for GPUs. And in order to support this tool, we will also develop a memory sanitizer specifically for the GPU because the memory sanitizer is also missing right now, which significantly blocks the research of developing detection tools. So that is the first thrust. And we know if we can detect and fix all the vulnerabilities ahead of time before the software is deployed, it's the ideal case. But in practice, it's very difficult. So on the other hand, we definitely want to make sure that even if our GPU software has vulnerabilities, they're not going to be exploited by a attacker, by a adversary. So in the second thrust, we're developing runtime GPU memory protection techniques. So specifically, we're looking to adapt the proved CPU side defense techniques to the GPUs. But we know since the GPUs, they have different execution models, different hardware designs compared to CPUs, then of course we'll have to tailor the designs to make sure they work the best for the GPU scenario. And we also want to make sure like our defense mechanisms are lightweight or deployable. So we're looking to implement these mechanisms as plugins for the GPU drivers and specifically GPU memory management units. So that's basically the overview of this project. And regarding the benefits to scientific cyber infrastructure, we believe this project will bring significant benefits. So first of all, for domain scientists, will provide usable and easy to adopt security tools. The vulnerability fuzzing and repair tools will definitely make sure like we conduct a usability study to provide the usable tool for the domain scientists who may not have a lot of knowledge, expertise regarding the low-level GPU design, the GPU memory safety issues. So that's for domain scientists. And on the other hand, for CI providers, we will provide deployable, ready-to-use runtime protection mechanisms, and we'll definitely make sure that our mechanisms are not bringing significant performance overhead, which is not something we want at runtime. So regarding the result sharing plans, first of all, we'll definitely open source all the tools we develop in this project with the public, and we will definitely provide comprehensive documentation. And we have also secured unfunded collaboration with CI providers from PNNL, the National Lab, and also Microsoft. So we will collaborate in terms of the mechanism deployment and integration. And regarding the vulnerabilities we discover using our detection tool, the fuzzing tool, we'll definitely disclose all the vulnerabilities to the AI software development teams through the standard disclosure procedures so that they can actually fix the problem on time to help all their users. So that's the project. And for the data sharing plan, so we have two things to share. So first of all, we have all the tools we developed to share. So like I said, we have a AI GPU code fuzzing framework with a memory sanitizer, and we also have the runtime memory protection mechanisms, which are implemented as GPU driver plugins. So that's the tool. On the data side, we don't have much data to share. Is again not a data intensive project, but we do have some good data that we're really willing to share. So first of all, we will have fuzzing results. So like I said, we will definitely report the vulnerabilities to the development teams. But on the other hand, we would also like to maintain a data set about it because we believe it's gonna significantly benefit future research in this area. And we would also like to share the synthetic data we develop in order to test the functionality, the effectiveness of our protection designs. So in terms of data sharing, I actually just had a meeting with the OSDF folks this morning with Brian and Christina. Thanks for meeting with me, by the way. So I think we have figured out a good plan for the data sharing, and right now we're just figuring out how to get things started. Yeah.
Fantastic. That's great. Great stuff. This is, I mean, another compelling thing that I think will really benefit a ton of scientific cyber infrastructure. I think you're spot on with the data sharing plan, especially the synthetic testing. One of the challenges you're going to face is like, okay, what is the cost, right? As you mentioned a couple of times, this is the lightweight, and so if there's common benchmarks, that's where an NDP and an OSDF can maybe help to find good shared benchmarks. But great stuff. Any other quick question? Otherwise, I think this is off to a great start and good plan.
Maybe one
Sure.
follow. One is indeed, Yanan, when's the award for the program of the first person to put together a meeting with Christina and reach out? So it was great to have a chat with you. But second, for you or for anybody else on the call that's thinking about fuzzing, at the first talk we talked about the OS pool, and that's a great example of if you had a setup that could fuzz for 10 million, 100 million hours, GPUs or CPUs, there's quite a bit of capacity for things out there like fuzzing, which is a great example of something where just the more compute you throw it at, typically the better it gets.
Excellent.
Thank you.
Thanks.